Hello students, we are going to review question 1 of the Synoptic Tutorial 1 given to you a few days ago. For question 1a, we have the major ingredient of marijuana, this compound known as THC. You are given this particular isomer when the CC double bond outside of the phenolic OH ring is at carbon, is between carbon 1 and 2. Okay, and you were told that THC and its enantiomer shows two absorption, 273 and 279 nanometers respectively, and with their respective extinction coefficient. The first part asks you to identify the chromophore in the THC molecule. So the first thing we need to do is to recognize the fact that for THC molecule, there is a highly conjugated system that's around the phenyl ring, and at the same time you also recognize that the two oxygen bonded directly to the phenyl ring, in this case one of them is the phenolic oxygen and the other one is the oxygen belonging to the ether linkage directly bonded to the phenyl ring. They contains lone pairs of electrons which can potentially delocalize into the phenyl ring. So this potential delocalization will further narrow the HOMO-LUMO gap, or the energy gap between the energy level where electronic transition can take place. So essentially that's largely the HOMO-LUMO gap we are talking about often. Okay, yeah, so I would identify the chromophore as the phenyl ring together with the phenolic OH, or you can just simply say that the phenolic group is the one responsible as the chromophore in the THC molecule. For part 2, you were asked how would you expect the UV spectrum of the other isomer, delta 2 THC. You were told that delta 2 is the isomer with the CC double bond between carbon 2 and 3 instead. So what we can do is instead we have a CC double bond between carbon 2 and 3, and it's going to be conjugated with the phenyl ring. Yep, so I'm just going to erase this and then draw a new CC double bond between carbon 2 and 3, and when it is conjugated it will further narrow the HOMO-LUMO gap. Because of that, you know that the energy of the gap is equals to hc over lambda. Yep, so a smaller gap will mean that it will absorb at a longer wavelength. Okay, so with this particular idea in mind, you should be able to highlight to the examiner that number 1, the system become more conjugated due to the fact that C2 and C3 double bond will be conjugated with the phenyl ring, and then this is followed by the fact that the greater in conjugation will narrow the HOMO-LUMO gap, and because of that you expect the absorbance to occur at a longer wavelength. Okay, so that is how you link up and draft your answer. And then for the last part involves some calculations. You were told that in some clinical trials the enantiomer of THC has been administered as an intravenous saline drip, and then the dripped solution shows an absorbance of 0.954 at a wavelength of 279 nanometers in a cell of path length 1 cm. This should be a relatively straightforward calculation because you are simply just asked to use Beer's law to calculate the concentration of the enantiomer in the dripped solution. Okay, so you know that Beer's law is A, the absorbance is equals to epsilon CL. Okay, and since it has an absorbance of 0.954, yep, this is equals to what about the extinction coefficient? Oh, it's given to be over here 2010, because if it absorbs at 279 nanometers you should be choosing 2010, so make sure you choose the correct number. So this will be 2010, okay, multiplied by the concentration and then multiply by the path length, which is 1 cm, so that would be 1.0. Yep, so you can easily get the answer to be 4.75 times 10 to the power of minus 4 moles per dm cube. Okay, so just make sure that you punch your calculator properly in order to get the correct answer. This should be a relatively straightforward application of Beer's law. Okay, then we'll move on to question 1b. You are asked to study the following synthesis of THC and answer the questions that follow. Okay, earlier on I forgot to mention that question 1 was an old A-level question, so it's a 2010 A-level question. Yep, we have modified a little bit, add a little bit of flavor into question 1b so as to elevate its difficulty just a little bit. Okay, if you compare to the old A-level question, there isn't much difference. Yeah, so we only added a small part. At this moment I can't exactly tell you which small part we added because I mean, it has been quite a long time. Okay, but it doesn't really matter because everything follows your curriculum as well. Okay, yeah, so let's take a look at the synthesis scheme first. Yeah, so first of all, you have this molecule with 2-phenolic OH and a carboxylic acid, 135 position. Yeah, so reaction 1, you notice that after reaction 1, the 2-phenolic OH are being transformed into methyl ether. Okay, and then after that, in step 2, you notice that the carboxylic acid is being transformed into an acyl chloride. Yep, and then in step 3, you notice that the acyl chloride is now being transformed into a ketone. Okay, so this is the R group. It has a long chain over here. Yep, and then after that, you notice that the ketone undergoes some sort of a reduction. How do I know it's a reduction? Because the oxygen is being removed, and then that original carbon is being replaced by 2 OHs. Okay, this is a reduction which is not in your syllabus. You have not learned it. If you want to find out a little bit more, you may look up either Clemmensen reduction. Okay, Clemmensen reduction is spelled as Clemmensen, either Clemmensen reduction or Krishna reduction. Yeah, both of these reaction conditions will work in our case here. Yeah, Clemmensen reduction uses a very acidic condition. In our case here, the presence of the ether group shouldn't affect. Krishna is slightly basic, so it's fine as well. You can look out for these two reactions if you are interested. If not, you won't be asked anyway. Yeah, you are probably asked what kind of reaction is that for. I think later on part 2 asks you the type of reaction occurring in steps 3 and 4. Okay, then in reaction 5, you notice that the ether is being removed. Okay, yeah, and then it's being removed, and it gives you back the phenolic OH. Yeah, and then after that, you notice that from W to THC, it began with some form of nucleophilic addition, or is it nucleophilic substitution, or is it electrophilic substitution? That is for you to decide. Yeah, but obviously over here you notice that it involved the phenyl ring because the H is lost eventually. Yeah, so since it involved the aromatic phenyl ring, you know that it should be some form of electrophilic substitution. Yep, and you notice that Lewis acid is not used except for H+. Okay, you can easily understand why this is the case because of the fact that the 2-phenolic OH will activate the ring towards electrophilic substitution. Okay, and then of course along the way after that, you notice that this particular intermediate is formed, and this is followed by the phenolic OH attacking this particular position and eventually giving you the tricyclic system. Okay, I think later on you are asked to illustrate the mechanism as well. Okay, yeah, so we are just going to look through the questions quickly. First, for part 1, we are asked to suggest reagents and conditions for reaction 1 and 2. This shouldn't be difficult because number 1 is I'm going to replace the H here, okay, with a CH3. At first, you might not know what you are getting yourself into, but if you could remember, the phenolic OH is acidic because it has a relatively acidic proton. pK is about 10, so we can easily turn it into a nucleophile. So step 1 is actually a form of nucleophilic substitution. Yeah, so because of that, I expect perhaps you can first begin by introducing sodium hydroxide. Okay, so you can introduce sodium hydroxide perhaps in the solid phase. Yeah, so along the way, it's going to deprotonate the H, and then you're going to get the phenoxide anions. Okay, then after that, you can easily introduce an excess methyl iodide. Okay, so excess CH3I. You can choose to use CH3Br if you want, or if not, then you can also use CH3Cl. Yeah, but CH3I will result in a faster reaction, as well as it will require a milder condition. But this is usually not a consideration in H3 or H2, especially for novel reaction. Yeah, if you wish to, you can just include heats. Okay, so that the reaction will go faster. Okay, in our case here for CH3I, I think heating, elevating the temperature a little bit will ensure a faster and more complete reaction. Yep. Eventually you might want to restore the acidity by adding some sulfuric acid or HCl. The reason being, in the initial phase you introduce sodium hydroxide. Yeah, so because of that, you want to ensure that the system regain its proton. Of course, in an actual synthesis, you don't really need to include the acid because it is understood as a workup step. Yeah, but if you could remember, for H3 kind of exam, you might just want to include it for completion's sake. Okay, and then for part 2, it will be quite straightforward because you are merely converting a carboxylic acid into the acyl chloride. Yeah, so you can easily achieve this by using PCl5 solids, okay, at room temperature. Okay, yeah. Then the next part 2, you are asked what type of reaction are involved in step 3 and 4. I think we have already discussed step 4. Step 4 is a reduction, so you can just write it into your answer. For step 3, you'll notice that the Cl is being replaced by the long LQ chain. Yeah, this is not a nucleophilic addition, okay, so you have to be a little bit careful here, because in the case of nucleophilic addition, you notice that the eventual product, your carbonyl carbon, the carbonyl oxygen will become an OH. Yeah, so this is more of a nucleophilic substitution because the Cl is being replaced by the R group. Yeah, so usually we use a Grignard reagent for such a reaction, but Grignard reagent is not in the H3 curriculum, so normally we don't ask you what you are expected to add for step 3. Okay, then for part 3, you're asked the question which earlier on I've highlighted over here. Okay, 2 methyl group are added in the molecule in reaction 1. You notice that the methyl group is added via nucleophilic substitution, and then they are removed in step 5. So you will ask, why is their presence necessary in the greater scheme of things? Okay, this can be a relatively straightforward question, or it can be seen to be as a difficult question. Okay, but what we need to do here is really to examine steps 2 and 3. Okay, so remember that for step 2, you are converting the carboxylic acid into an acyl chloride. Now imagine that if the phenolic OH is present, what will happen to the final compounds? Yeah, you will expect some form of an intermolecular reaction between one of the acyl chloride and the phenolic OH of another reagent. Yeah, so eventually you're going to end up with a lot of esters, or a mixture of esters being formed, and you don't want that to happen because you want to ensure that the acyl, after the carboxylic acid has been converted into the acyl chloride, you want the nucleophilic substitution to take place so that the acyl chloride will become the ketones. You want that to happen, and you don't want the side reaction where ester formation is going to take place. Yeah, so because of that, you have to make sure that all the phenolic OH group, they are not there to react with the acyl chloride. Yeah, so in order for you to do that, you need to do some form of protection. Okay, so the protection mechanism is basically just to convert the phenolic OH into a methyl ether. Yeah, and after you have done the conversion, the methyl ether will not mess up your reaction later on by reacting with the acyl chloride to give the ester. Okay, so a very short answer you can give for part 3 will be it's more of to prevent the reaction, or to prevent the side reaction between the phenolic OH and the acyl chloride formed in step 2. Yeah, and how do we prevent the reaction? We prevent the reaction by converting the phenolic OH group into methyl ether groups, because methyl ether do not react with acyl chlorides. Okay, so with that, I think you should be able to understand why step 3 is necessary, or rather why is the first step necessary, although they are being removed in step 5. Yeah, in chemistry we call this a protection group. So the protection group essentially prevents that group from reacting with the other reagents being added. Yeah, once the protecting group is not needed, it will then be removed. Okay, then we're going to move on to step question part 4. In the last step of this synthesis, citral is protonated before reacting with W. Okay, so you were told that citral is protonated. Protonated at where? Obviously at the carbonyl oxygen. How do I know? Because the protonation at the carbonyl oxygen will generate a stronger electrophile, so that electrophilic substitution will take place. You may then argue that, oh, I have the phenolic OH group which donates electrons to the phenol ring, etc. Then so you expect electrophilic substitution to take place anyway, right? Yeah, but in certain cases we will never know whether the electrophile is a good enough electrophile. So in our case here, the experimentalist or the chemist realized that I might need to generate a stronger electrophile, and that's why the H+ is being introduced. Okay, yeah. Then and then you were told that it reacts via a series of reactions to give intermediate X, and the X is then protonated and then loses water to form a carbocation. You were told to suggest a structure for the carbocation and hence a mechanism to produce THC from W. So we want the mechanism from W all the way to THC. Okay, so right now how are we expecting this to work? Okay, so the first steps, I'm just going to illustrate for you the mechanism. Okay, so the first step, we need to draw citral. Okay, so citral is likely to look like this with the carbonyl oxygen, and then we have the alkenes over here. So remember that the carbonyl oxygen contains the lone pairs of electrons, and then we have the protons over here. So we expect the carbonyl oxygen to be protonated. Once it's protonated, the carbonyl carbon will be more electron deficient, so therefore more susceptible to electrophilic substitution, which is the reaction we desire. Okay, then after that, I'm going to draw out the one with the phenol ring. Okay, so the OH here, and then I'm going to draw out the phenol ring. Okay, so I'm going to draw it the other way around so that later on when I push my electrons, it's easier. Okay, and then the OH. Okay, so when I push my electrons, in this case, I'm going to use red. Okay, so we know that it's going to be substituted at this particular position. Okay, so remember that once or rather remember that whenever we push electrons, we always push from the electron source to the electron sink. So now the electron sink is the carbonyl oxygen, or the protonated carbonyl oxygen. So we're going to push from the source, okay, all the way to the sink. Okay, now the sink is over at the oxygen. Okay, then I'm going to redraw the structure. Okay, I'm going to just draw it really quickly so it's not going to look very nice, so pardon me for the not so nice drawing. Okay, the OH is like this, and then oops, I'm just going to maybe draw the OH out like this. Okay, so this is the OH. Okay, and then I'm just going to draw out the rest of the phenol ring. Okay, with the double bond OH with a plus charge. Remember to draw in the plus charge. Okay, and then of course the OH here, and then and the R group. Okay, so please check your structures against mine to see whether is it consistent. If not, then you might want to modify it along the way. Okay, and remember that there is a H over here. usually for electrophilic substitution, the H will be lost. Okay, so we are just going to continue pushing the arrows. Okay, so as to restore the aromaticity. So I'm going to restore the aromaticity like this. Okay, so this will allows the proton to be lost. Yep, after the proton is lost, I'm just going to redraw the structure out for you, and then it's going to look like this. Yep, and then the OH is still hanging around, and then I'm just going to draw out the aromatic ring. Okay, the aromatic ring OH. So now the aromatic ring is intact. I probably don't really need to do much about it. Yep, then after that, you were told that X is then protonated. Okay, where is X? Yeah, so this is the intermediate X. Okay, X is then protonated and then loses the water to form a carbocation. Okay, so we need to make use of this clue to help us continue the mechanism. Okay, then of course I'm going to just incorporate a proton here. So this proton is here. Remember that the OH group contains a lone pairs of electrons. I'm just going to protonate the OH group, yeah, because that is probably the only group which can be protonated. Okay, and then I'm just going to redraw the whole thing. Okay, my apologies, it's going to take a bit of time, but I'm just trying to do it ASAP. Okay, and then the OH is here, the OH is here, and then the OH2 with a plus charge. Okay, and then the R group is here. Okay, now the first thing you might be thinking is, okay, I'm going to lose the water. Okay, so let us try losing the water first. Okay, so I'm just going to lose the water molecule. Okay, so after I lose the water molecule, remember to write out minus H2O. I'm going to generate the carbocation. Okay, so let's try and take a look at our carbocation. So I'm just going to generate the carbocation first. Okay, and then with a plus charge over here. Okay, I'm just going to draw the rest of the phenol ring out. Okay, like this, and then the OH, and then the R. Okay, so is this the carbocation that is expected of us? So that's the question we might want to ask ourselves, because the question is suggest a structure of the carbocation and hence suggest a mechanism to produce THC from W. Yeah. So the question to ask ourselves is this the most stable carbocation, or do I need to draw the relevant resonance structures? So for example, some of you might be thinking, can I be drawing the resonance structure where the lone pairs, or rather where the CC pi bond delocalize, and then I form a tertiary carbocation? Yeah, so the answer is no. This is the carbocation which you should be drawing, because this is what we call a benzylic carbocation, and the positive charge is likely to delocalize into the phenol ring, because the empty p orbital on the carbocation will be able to form a continuous overlap with the pi electron clouds of the phenol ring. Yeah, so this is the likely to be the most stable carbocation, so we'll just leave it as it is. Okay, yeah, is that alright? Okay, so the next thing, I'm going to erase the plus charge. I'm just going to shift it into a strategic position, maybe a little bit more inside. The reason why I'm doing that is because I'm going to continue my arrow pushing. So I'm going to push the pi bonds into the carbocationic carbons to form a tertiary carbocation at this point. But you know that once I form the tertiary carbocation, what is likely to happen is that the lone pairs of electrons on the nearby phenolic OH is likely to attack it. Okay, so I can draw them in one concerted manner, and it is likely that they occur in one concerted manner as well. Number one is because the carbocationic carbon is the electron sink, and the lone pairs of oxygen on the phenolic OH is the electron source. Okay, and once I do that, I'm going to form the tricyclic structure, which will look like this. Okay, so I'm just going to draw it out first. The tricyclic structure. Yeah. I'm just going to do it quite quickly. This is the oxygen, and then and the phenol ring. Okay. Sorry, I think I'm just going to redraw it again. This portion doesn't look very nice. Okay, so I think I need to draw it a little bit sharper, so that I do not misrepresent the structure in any way. Okay, I think this will make a little bit more sense. Okay, like this, like this, like this, and then like this as well, and then there's a pi system here, and then the OH, and then the R groups, and then of course there's a H here, so this is a plus charge. Okay, and of course the final structure will be THC, right? So I'm just going to lose the protons, okay, minus H plus, and you can then draw the structure. I don't think you need me to draw it. Okay, some of you might ask, if I can draw this portion in two separate steps, which means the pi bond attack the benzylic carbocation first to generate a tertiary carbocation at the end propanol-like group over here. Over here, you might be asking that, can I generate a tertiary carbocation first and then the phenolic OH attack it? No problem, you can do that if you want to. Yeah, remember that you're supposed to propose a mechanism. A reasonable mechanism will do, not something overly complicated. Okay, so certain steps you can combine, certain steps you can draw them out separately. It's not a problem. But you need to understand why you do certain things. Yeah, so once you understand that, then I think it's a lot more clear cut. Like for example, in the initial step, you cannot protonate the carbon oxygen together with drawing this portion. Okay, it is not legitimate for you to do that, because in most cases the protonation must come first before you generate the more stable, or rather the more reactive electrophile, before electrophilic substitution takes place. Yeah, so there is often some logic behind why we push arrow in a certain way. Yeah, so whenever in doubt, you might want to consult your teachers about it so that we can clarify. After all, we are a little bit more experienced than you guys. Okay, then finally we have part 5. It's supposed to explain why this synthesis produces a mixture of the two enantiomers of THC and suggest a method by which they can be separated. So the key question here is, why the synthesis produce a mixture of two enantiomer? We can easily understand it from this particular step, which involved a carbocation. So where is this step? Yes, this is the step. Yeah, so remember that the carbocation has a trigonal planar geometry about the positively charged carbon. Yeah, so that means that this particular pi group, I'm just going to highlight it, this particular pi group, right, can attack it from the top or bottom face with near equal probability. Yeah, so remember that this structure is a little string-like. Okay, so and it's flexible, it's like a rope. Yeah, so it can either be tilted up a little bit high and approach it from the top face, or it can tilt a little bit lower and approach it from bottom face. Yeah, so the top and bottom face attack is, in this case, probably near equal probability. Yeah, and this will result in the formation of two enantiomers, or the formation of an enantiomeric pair. Yeah, and you will ask, what is a good method to separate them? We can use chiral column chromatography. For the chiral column chromatography, right, the column is packed with reactants, or not exactly reactants, but substances that are chiral as well. So they will interact a little bit differently with the two enantiomer. Yeah, so the slight difference in interaction will cause one enantiomer to elutes out from the column at a slightly slower rate. That means that it's a bit like you are walking through a crowd of people, and then suddenly you met your friends at one of the shops, and then you will just stop by and talk to them, and then other peers who don't know these people will just continue walking. Yeah, and therefore you can view the friends, the friends at the shop whom you met as the chiral column, where they can form a stronger interaction with you, and then your other friends who don't know them, weaker interaction, so that they will just walk through it. Yeah, so this is how column chromatography, how chiral column chromatography works. You might not have learned this at your current curriculum. Yeah, but it will be good to know that a good method to separate an enantiomeric pair is by chiral column chromatography. We can also accept other answers, such as fractional crystallization, but again, for crystallization, you need to ensure that there is a group where it can be used to react with another reagents. So usually for fractional crystallization, we are looking at, say, a carboxylic acid or an amines with a reagent that is chiral, and it also contains a carboxylic acid or an amine. Yeah, you usually don't do fractional crystallization by forming a totally different compound. Usually we don't. I mean, sometimes we do, but usually we don't. Yeah, so the most convenient method is still chiral column chromatography. Yep, so that will be the end of the review for question 1. I hope you have learned something from it, and then we'll look forward to review other questions with you in the next videos.